Okay, sorry, I don't know why the video recording cut out on me. But to continue with Chapter 1, we're almost done. Estimation of energy expenditure. Again, when we're talking about quantifying work on a treadmill and determining its energy cost, we also have a couple other things to take into account, and that's the oxygen requirement increases as the linear function of speed. So if we need to convert VO2 max into a amount of time to take into account the increases in oxygen requirement, then we can take the VO2 max and we can convert it in its equivalent, which in this case walking 0.1 meters per minute, which is referring to the oxygen consumption, adding in 1 met, which is your metabolic rate, and in the case of running it's 0.2 meters per minute, and then adding in 1 metabolic equivalent again, because again that's your basal metabolic rate. Okay, so it's really the same calculation. We just understand that running economy or just exercise economy changes from walking to running. That transition is still a point of research, but we understand that with walking there's a certain amount of oxygen requirement with that, and it's a little bit flatter over here, whereas running, based on running economy changes and the efficiency of the individual, the volume of oxygen consumed increases. We take into account their metabolic rate, and then it's a little bit steeper of a slope right here as we take into account the running speed, or the duration of time rather. Okay, estimation of the oxygen requirement of treadmill walking. Again, I already went over that. If you just have the VO2 max of the individual, make sure that you take into account the linear progression of speed. So take the VO2 and quantify it as 0.1 ml per kg per minute and divide it by meters per minute, meaning taking into account the amount of time, multiplying by the speed, and then adding in the metabolic rate again. So to make that a little bit more clear, if we go back, again, we're always taking into account this linear function of speed. So in the case of walking, we have the VO2, but we have to quantify it or denote it as 0.1 multiplied by meters per minute. So if we actually do the calculation, we have 0.1 mLs per kg per minute, and in this case it should say multiplied right here, but they did meters per minute right here, so then you have to denote it as a quotient. But you're always multiplying again by the rate of speed, and then you have the metabolic rate that's taken into account. So if somebody's walking at 80 meters per minute, that's the rate at which they're walking, we first take into account the conversion of VO2, which is 0.1 mLs per kg per minute. We multiply by the rate of speed, or the rate of time rather, 80 meters per minute, and then add in their metabolic rate, which is 3.5 or 1 met, and then we have 11.5 mLs per kg per minute, which we know that to be a VO2 quantification. And then we take their VO2 max, 11.5, and if we want to convert it to mets, divide it by 3.5, which is 1 met, and then we have 3.3 metabolic equivalents. And then you do the same thing for running, except instead of 0.1 you have 0.2 to take into account running economy changes. But in any case, you multiply 0.2, which is the standardization for VO2, multiply the rate of time, or the speed, add in the metabolic rate, then you have VO2, you divide it by 3.5 to convert it to mets, and then that's 10.2 mets. Okay, and you can do the same thing with cycling as well. Estimation of the oxygen requirement of cycling. It's comprised of 3 components. You have your resting VO2, which is 1 metabolic equivalent, or 1 met. You have the VO2 for unloaded cycling, and you have VO2 of cycling against external load. So the best way to put this is the resting VO2, and the VO2 for unloaded cycling. This is basically cycling with no resistance. If there's no resistance on the pedal, then we quantify the oxygen requirement the same way we do with your resting VO2. But if we have to take into account an external load, meaning that you're pedaling against a resistance, then we have to take into the force that is being put on the flywheel. So for example, 1.8 milliliters per kilopond, and then you multiply by the work rate, and then you multiply, or I'm sorry, well, with the -1, then you have to divide by body mass. So if there's an external load, then we have to take into account that load in order to accurately calculate the oxygen consumption. So here's an example. So the equation is the work rate in kiloponds per minute. You have M, which is the body mass of the individual, in kilograms, and then 7 is the sum of the resting VO2 and the VO2 of an unloaded cycle. So a 70 kilogram man, we have the force of the individual, or the external force. We have the rate at which they are cycling, and then at that point it's just a simple product. You take into account 1.8, which, like I said, is the standard unit for cycling against an external load. You multiply it by the rate of the speed of the cycle, 600 kiloponds per minute, and then you multiply by 70 kilograms, which is the force of the individual, and then you add in 7, and then you have mLs per kg per minute, which is the unit for VO2 max. Okay, and this is the relationship between work rate and the VO2 for cycling. Again, it's a complete linear line, meaning that as the work rate goes up, the VO2 max goes up. And this makes sense. As the power output or the work rate increases, the demand for oxygen increases. As it gets more difficult, obviously you're going to have to consume more oxygen. And this is all to really determine exercise efficiency. The reason we need to be able to calculate these different things is we want to determine the efficiency of the individual, and we want to be able to determine the total amount of energy expended. So the net efficiency is the ratio of work output divided by the energy expended above rest. So really, if we want to determine the efficiency of the individual, we want to see what the difference is between how hard the work was versus how much more the work was over their resting metabolic rate, right? So the net efficiency of cycle ergometry is estimated to be about 15 to 27%, meaning that it's 15 to 27% greater than your metabolic rate, meaning that it's 27% more work output than when I am at rest. And the efficiency decreases with increasing work rate. And there is a curvilinear relationship between work rate and energy expenditure. Okay, and so here's an example, cycle ergometry of exercise. If the rate is 600 kiloponds per minute, then we divide that by 426. Again, that's determined to be another work rate, and in that case it's 1.41 kilocalories per minute. So this is the total work being performed in the activity, and then once we have the work performed on the cycle, then we need to determine the energy expenditure that resulted from that work. So we take into account steady state versus resting, which in this case is 1.5 minus 0.25. We take that difference, multiply it by 5 kilocalories per liter, so we have it in the unit of measurement that we want, which is 6.25 kilocalories per minute. That's the net energy expenditure, and then we can determine the net efficiency. So if we have the work rate on top, and we have the net efficiency underneath, the quotient of the two multiplied by 100, that's how we get the total amount of exercise efficiency. So in this case, if a person is exercising at 600 kiloponds per minute, then they are at an exercise efficiency of 22.6 when you determine the amount of energy expenditure. Okay, so exercise and efficiency is important to understand because it's going to vary from individual to individual. There are a lot of factors that influence your exercise efficiency, and this is the work rate of the exercise, the speed of the movement, and also the muscle fiber type, which is ultimately influencing your exercise metabolism. Obviously, as your work rate goes up, as the exercise becomes more strenuous, your exercise efficiency is going to go down. As the speed of the movement increases and ultimately your power output increases, exercise efficiency is also going to be affected. And depending on the muscle fiber type, there are some fiber types that are more efficient than others. Type 1 muscle fibers or oxidative muscle fibers are much more efficient than, say, type 2X muscle fibers, primarily because type 2 muscle fibers are subject to much more fatigue. So in all three of these factors, the central component here is what is the rate of fatigue. If there's an increase in work rate, then there's probably going to be more fatigue. If the speed of the movement increases, then the person is going to experience more fatigue. And then if they have a muscle fiber type that is less fatigue resistant, then that's going to also influence their exercise efficiency. And it makes sense, this is this table right here, or this graph right here, is just showing that as your work rate increases or the amount of watts goes up, then your exercise efficiency goes down as your work rate increases. And really the factor here, if we were determining, the work rate of a robot, then it would be absolutely horizontal because fatigue would not be a factor. But in individuals where, your exercise metabolism and your fiber type density has an influence on the amount of exercise that you can perform, then we have to take into account fatigue, and like I said, that's going to influence your overall exercise efficiency. All right, and the relationship between energy expenditure and work rate, it's actually an inverse relationship now. As the work rate increases, the energy efficiency goes up. And again, this is the work rate right here, and notice that it's somewhat exponential. We have a period of time where we can keep up with the work rate in a linear fashion, but at a certain point, the exercise efficiency goes down as the work rate continues to increase, and as our exercise efficiency reduces, that's going to result in higher energy expenditure. And this is the effect of speed of movement on net efficiency, and what you'll notice is that this is more of a bell curve. So if exercise is performed at a very low speed or a very low rate of movement, then there's not going to be much net efficiency, meaning that if I'm pedaling extremely slowly on my ergometer, then I'm not going to have much efficiency there. It's just not a very comfortable pace, but there seems to be more of a rate that is more comfortable for the individual, in which they can reach the maximum amount of net efficiency. But as you increase the speed of the pedal, as you pedal faster and faster and faster, that's going to affect your exercise efficiency. So know that pedaling slowly, yes, you are performing less work, but it's affecting your exercise efficiency, and it's ultimately going to result in more energy expenditure. There is an optimal speed of the movement, and it's not just pedaling on a cycle, it's also walking and running as well. There's an optimal speed in which you have the most exercise efficiency and therefore the least amount of energy expenditure related to the amount of work that you're doing. So that last point is really just leading into running economy. Your running economy is very much based on the speed of the movement, the mass of the individual, and the fiber type density of the individual. So it's not possible to calculate efficiency of horizontal running. Again, if you want to determine the work, you have to have a distance, and the only way you can have distance when it comes to running is if you have vertical displacement. So this is all just kind of an estimation. It's not an exact amount because you can't technically measure it. So in place of that, we have running economy. It's the oxygen cost of running at a specific speed, and a lower VO2 at the same speed indicates better running economy. So for example, if you have one person running at 3 miles per hour and another person, well, that's a little too slow. If you have one person running at 7 miles per hour and another person running at 7 miles per hour, and person number one has a lower VO2 max and less oxygen consumption than person number two, even though they're running the same speed, the person with the lower VO2 max, or the person with the lower oxygen consumption, is considered to have a better running economy and better exercise efficiency. And this is really based on individual differences. Elite runners are considered to be about 10% more economic when compared to less trained runners, and 20% difference between most and least economical runners. So basically, what makes an elite runner, yes, there are some physiological factors there, but really it's their running economy and their ability to utilize energy effectively and to not be at the same energy expenditure even though they're running at the same pace as somebody else. Okay, and these are oxygen cost of running in different categories of runners. What you'll notice, untrained versus elite, the total oxygen consumption is just much lower, really in every category, minimum, the mean, and the maximum, meaning that they're performing the same amount of work, but the oxygen consumption is much lower in elite runners versus untrained runners. And again, this is because of changes in running economy. Okay, that is chapter 1. Email me if you have any questions, and make sure that you take the chapter 1 post-lecture quiz.